Welcome back. In the last segment, we established that we need to use rockets. That is, unlike airplanes, rockets bring all of their own fuel with them. So next, let's look closely at different kinds of rockets. All rockets that are used to launch objects to space are chemical rockets. That is, there is a chemical reaction creating the force needed to lift the rocket up off the ground. There are two types of chemical rockets, both of which can be seen in the image of the space shuttle. The first is the two solid rockets on either side of the space shuttle. Those are the white cylinder with pointy tops. The second is the reddish-orangish external fuel tank. This is carrying liquid propellants. So both these solid and liquid rockets are mixing chemicals to create energy. So don't worry about this word chemical. This is exactly the same idea as what's going on in your car engine or in an airplane. In those cases, we mix gas, fuel, with air, and a chemical reaction happens when this mixture is ignited to make it go forward, to create energy. And both solid and liquid rockets use these chemical reactions to create force. The chemicals that they use are in different states. One is liquid, one is solid. So before we explore liquid versus solid rockets, let's take a second to write down what we might actually look for in a good rocket fuel, like what makes a good rocket fuel. So the first thing we want to have is high energy. That is, we want something that creates a lot of force, a lot of oomph. At the same time, we want something that is lightweight. And that's asking a lot, right? We want something that creates a lot of force, but isn't all that heavy. We also want to consider cost of the rocket fuel. We always want things to be cheaper. And then finally, we want something that's easy to store and handle, something that isn't super toxic and is safe, or at least safe enough given that at some point we actually want it to explode. It turns out that chemical rockets are the only type of rockets that fulfill all of these requirements when we're launching rockets from Earth. There are other alternatives, like nuclear reactions or electrical ionization processes, but for very different reasons, these alternatives can only be considered once we're actually in space. And we'll talk about those alternatives to chemical rockets in a later segment. But for launching rockets from Earth, we are stuck with just these chemical rockets. And so let's take a look at them in detail. Chemical rockets consist of a fuel, something to burn, and an oxidizer, something to react with that fuel. Together, the fuel plus the oxidizer are called propellants. And when these propellants are mixed together and ignited, there's a chemical reaction which creates force. Propellants can be stored as liquids or as solids. And since the engineering for handling liquids versus solids is different, this leads to two different types of rockets: liquid rocket engines and solid rocket motors. And note that the word engine is used for liquid propellants and motor is used for solid propellants. And I'm sure there's some curious history as to why these have different words, but here it's just cool knowledge that you can pull out on trivia night. For liquid rockets, the propellants, the fuel and the oxidizer, are stored separately and then are mixed together just before ignition. For solid rockets, the fuel and oxidizer are mixed together in a single solid that can be stored safely, and then the whole thing is ignited, kind of like a firework. So let's first look at liquid rocket engines, and then we'll compare them to solid ones. Liquid rockets are most similar to airplane jet engines. In a jet engine, air is mixed with the fuel, and that mixture is ignited in a combustion chamber. For liquid rockets, the air is replaced with an actual tank of oxidizer, and this is usually liquid oxygen. The oxidizer is mixed with a fuel. A common rocket fuel is liquid hydrogen or liquid kerosene. And these propellants, the oxidizer plus fuel, are combined in a combustion chamber and ignited to create the force that'll push our rocket up out into space. And you might ask, why are these propellants stored as liquid? When we think of, say, oxygen or hydrogen, you might think of them in gaseous form. However, when you get these gases really, really cold, they'll liquefy. And in the liquid form, the propellants are more dense and it makes for a more powerful explosion. There was a huge amount of work in the 1950s and 60s trying to figure out what combination of fuel and oxidizer was most efficient and produced the most amount of force. And so here is a table, a chart, of the different kinds of liquid fuels and oxidizer combinations. Rocket fuels are typically judged on something called specific impulse, or ISP. And for our purposes on the chart, higher is just better. So for example, in blue are fuels that are combined with liquid oxygen. And the winner in this category is liquid oxygen combined with liquid hydrogen. And there's certainly other kinds of combinations regularly in use. Many companies are currently using liquid kerosene or methane, and combined with liquid oxygen, this is usually a little bit cheaper and has a tendency to explode a little bit less. So coming back to how liquid rockets work, once you've chosen the fuel and the oxidizer, these propellants are injected into a combustion chamber and ignited. And a good thing about liquid rockets is you can control how much propellant is coming into the combustion chamber. That is, you can turn things on or off as needed. A few bad things about liquid rockets. So storing liquid fuel requires extremely cold temperatures, think like minus 100 degrees below freezing. So the fuel is usually just loaded into the rocket before launch. So if you need to scrub a launch due to weather or something like that, things can get annoying. On the flip side, liquid propellants are very reliable to ignite. That is, a mixture of liquid hydrogen and oxygen really likes to explode. And this is great for the moment you are trying to launch a space vehicle, but before that moment it presents safety challenges, and you need to keep these propellants very separate. In contrast, we turn to solid rockets, which are much safer on the launch pad. So, in a solid rocket, the propellants are mixed together in a factory and stored together as an inert solid. That solid can then be ignited. And a common example of a solid rocket is a firework. A firework has the oxidizer and the fuel mixed together, and then you light a fuse in order to propel your rocket or your firework forward. Similarly, just a lot bigger, is the white solid booster rocket from the space shuttle. Here we are looking inside the space shuttle solid rocket, and that ring of black stuff is the solid rocket fuel. The rocket is ignited from the inside and it burns inside out. Similar to a firework, once a solid rocket is ignited, you can't stop it. And this is definitely a disadvantage as compared to liquid rockets. While you can't turn it off, you can be super clever and control the rate at which a solid rocket burns. Since a solid rocket is burning from the inside out, it's the shape of that inside area, the inside surface area, that controls how fast it burns. So if you change the inside shape, say from a cylinder to a star, you have some control over how fast the burn is actually happening. It's like super clever. It's not something I would have come up with. But another disadvantage for solid rockets compared to liquid rockets is how much force they produce. So coming back to the chart of how much energy each rocket fuel combination creates, our solid rockets are way down there. Solid rockets do not create as much force as liquid rockets. And so you might ask, why solid rockets, why are they used at all? First of all, they are just safer on the launch pad. There's a much lower risk that a solid rocket will explode as compared to a liquid rocket when you don't want it to. You can also store solid rockets for longer. So once you've created your solid rocket, it can be stored for decades and still be ready to go at a moment's notice, which can certainly be useful in some cases. Okay, so now let's sort through the pros and cons of solid versus liquid rockets. For solid rockets, the pro is that they can be stored for decades and there's much less risk of explosion. The con is that once they're ignited, they can't be turned off, and perhaps most importantly, they're not quite as powerful as the best liquid rockets. For liquid rockets, the pro is that they're much more powerful than solid, and they're also more reliable to ignite. The con is that we need to add the fuel at launch, and there's just a much higher risk of failure of explosion. Given all of these competing issues, different teams have just made different choices. For example, the space shuttle uses a combination of solid rockets and liquid rockets using liquid hydrogen and liquid oxygen as propellants. The new Space Launch System, SLS, which will launch the Artemis mission to the moon in the next couple of years, again is also using a combination of both solid and liquid rockets. In contrast, the SpaceX Falcon 9 uses only liquid rockets, but a slightly different kind of fuel. They use a type of kerosene called RP1 and a liquid oxygen. This isn't quite as powerful as liquid hydrogen, but it's cheaper and it has a tendency to explode a little less. Another example is the workhorse family of rockets in China called the Long March. The Chinese Long March rockets use mostly liquid propellants too, but the fuel choices are slightly different. In particular, for the oxidizer, they use something different than liquid oxygen. Okay, so given all the pros and cons, everyone has made different choices about whether to use solid or liquid rockets. But again, these are all chemical rockets. The force is generated by a chemical reaction of the propellants when they are mixed and ignited. While these chemical rockets are the only type of rocket that produce enough force to lift our rockets off the ground, even here there's a limit that we're going to bump up against in the next segment. So as a final thought, we discussed last segment that airplane engines can't be used for space launches. That's because airplane engines are designed to use the surrounding air as an oxidizer, and there's no air in space. Let's turn that question around and ask, can we use rockets in airplanes? And the answer is we can, but generally it's a bad idea. So a solid rocket in an airplane is definitely a bad idea because once it's ignited, you cannot turn it off. And particularly for commercial airlines, that isn't great. You probably want some more flexibility than that. We could use liquid rockets in airplanes, and indeed there are military test airplanes that do use liquid rockets, especially when they're flying high enough up in the atmosphere where there isn't enough air for that chemical process. There's a couple reasons why liquid rockets aren't a great idea for commercial airlines, and they are rarely used in the military as well. So first, liquid rockets are just less efficient. Like, why carry an oxidizer with you when you can just use the surrounding air? And the second, perhaps more important, is that there's a real safety risk. Liquid hydrogen and liquid oxygen are incredibly good rocket propellants, which means they are incredibly good rocket propellants and they like to explode. While it's an acceptable risk for a rocket launch, the safety risk makes no sense for a commercial airplane. Okay, so now that we've discussed different types of rockets, in the next segment we'll figure out how much fuel we need to get into orbit and introduce my favorite equation, the rocket equation.